have a seat. The president will be with you shortly.
Kids these days, they expect to be hired without the minimum qualifications.
They're not too bad.
At least he's here. That's a start.
Hi, my name's Richard, and I'm the financial advisor here. And that's our president.
Enough chit-chat. Just tell him what he needs to do. I'm not paying you people to be nice to each other. There's money to be made. Come on.
Okay, Mrs. President, I'm just trying to get settled down.
Are you comfortable? Okay. I got the board all set up and ready to go. And Mrs. President, please be nice. He's new.
All right. Just give him his first assignment.
On the packet, we need you to design a parking lot with the largest area, find the maximum profit from our revenue and costs, and calculate largest volume of the cardboard boxes for our bottles.
Read the required skills page and tell me if you're up for this task or not. This is what I was talking about. Give this young man a quick rundown on how to do these tasks. Hopefully he will catch on fast enough.
Okay, let me see if I can pull up something from the last year's project. Oh, here's a good one. Okay, before I begin, there are two things that you need to keep in mind when you're doing optimization problem. First is the mathematical expression for the problem at hand, and the other is finding the local minimum or maximum from that expression. Okay, keeping that in mind, let's look at this problem. So, last year, we were working on fencing a plot of farmland next to the river. We had about 800 meters worth of fencing material. So from that 800 meters worth of fencing material, our president wanted us to find the largest area that we can enclose with that material. So let me draw you a diagram. And here's the river. This is the farmland. And this is the river. So we can see that the fence will only have three sides. Okay. So to solve this problem, we assigned x to this side, and the other side is also x since it's a rectangle. And the third side will be the total minus 2x, which is 800 minus 2x. So like I said before, to solve optimization problem, you need to first find the mathematical expression for the problem. And since we're looking for the largest area, it will be the expression for the area. A is equal to the width times the length. Okay, so now we have a mathematical expression for the area. Remember how to find the local minimum and maximum from the mathematical expression? Good. Okay. So simplified version of this expression is 800x minus 2x squared. And now we're going to find the local maximum since we're looking for the largest area that 800 meters worth of fencing material can enclose. So the A prime here is 800 minus 4x. Now, we need to find the value of x that will make the derivative of the area 0 for us to find the local maximum, right? Okay, so, and from this problem, we found that the x has to be equal to 200 for this expression to equal to 0. So, with that knowledge, we found out that the width has to be x, or 200, and the length has to be 400. And that the maximum area that we can get from that dimension is 80,000 meters squared.
Alright, you're good to go now, right?
No, Mrs. President, there's another problem we must address, profits. Do we have an example regarding that?
I'm sure there is. Let me look for it for a second. Oh, here it is. Okay. The data from last year suggests that our revenue could be represented by (16 times radical x), in which the x is in millions of units produced, and our cost could be represented by 4x squared, in which the x is also in millions of units produced. Okay, so our president asked us what the production level would be if we wanted to achieve maximum profit. Okay, now going back to the previous problem, what we had to do to solve the optimization problem was to find the mathematical expression first. Okay? So we looked for the expression for profit, which in this case is logically revenue minus the cost, or 16 times radical x minus 4 times x squared. Now, we need to find the local maximum from this expression right here. The p prime of x is, in this case, 8 divided by radical x minus 8x. And this had to equal to 0. And from that, we could solve for x, and it was equal to 1, or 1 million units produced. So we determined that in order to achieve maximum profit, we had to produce 1 million bottles and sell them. The interesting thing here is that by this point here, we're actually solving for x, where the derivative of the cost is equal to the derivative of the revenue. You can prove that this is the point where you will achieve maximum profit by sketching the two graphs. 16 times radical x looks something like this, and 4 times x squared looks something like this. This is the revenue, and this is the cost, which means the profit is revenue minus the cost, or the distance between these two lines here. As you can see, the distance between these two graphs is when their slope, or the derivative, is equal to each other. Anyway, there it is.
Are we done now?
No, the last problem has to do with finding the maximum volume for a newly designed box. Can you show him the work for our previous design?
Okay, let me look for it. Should be here, right here somewhere. Yeah, it is. Alright. So last design for our box was a bit small. So we used a piece of cardboard with the dimension 30-inch by 20-inch. So it looked something like this. And we cut out its corners so we can fold it up and make a box. The president wanted us to find the height that will give us the maximum volume. So these corners that we're going to cut out will be the height. So, to find the maximum value, once again, we have to find the mathematical expression for the volume, which in this case is volume is equal to the length, which is 30 minus 2x, or h, times 20 minus 2h, times h, or height. Simplifying this expression gave us 600h minus 100h squared plus 4h. Now that we found the expression for the volume, now we need to find the local maximum of that expression. The v prime is equal to 600 minus 200h plus 12h squared. Solving for h, that will give us 0 for our v prime. H was equal to 2 points, 3.92 inches and 12.74 inches. Now that we have 2 points, we need to determine which one is local maximum and which one is local minimum. Local maximum is when the derivative goes from positive to negative. In this case, the point 3.92 was where the value of v prime will go from positive to negative. Therefore, we found that this is the local maximum. So the dimension of the corners that we have to cut out in order to maximize our volume was 3.92 inches by 3.92 inches. Therefore, by putting in the value for 3.92 into the expression for the volume, we found out that maximum volume that we can get was equal to 1056.31 inches cubed. So that's how you do it.
Okay, Mrs. President, I think we're finished now.
Great, now go into the task specified on that paper. How well you do on this task will determine the length of your stay.
What a tough first day at work. Crazy president we have at our company. Anyways, I never realized how important optimization is in the business world. I learned that optimization can be used for various purposes: maximizing area, designing a box with maximum volume, finding maximum profit, and much more. Optimization can be incorporated into business and economics, and hopefully this new skill will help me become a more valuable employee.